Okay, so we're going to go over R1, graphs and equations. Okay, so the book is split into 7 chapters. Okay, and R is basically a review chapter. Okay, the R is the review chapter. So they call it R.1. And here we're going to be doing graphs, okay, and equations. Okay, graphs and equations. An intro to graphs and equations. Okay. Okay, let's graph a line, shall we? Woohoo. We're starting hard. Okay, let's graph the line y equals 2x plus 1. Nice, nice. Okay, so I'm going to do a little something called a T-chart, x and y. Okay, if I go too fast, just let me know that I'm going too fast. I tend to speak pretty fast. Okay. Okay. If you're like, I'm trying to keep up and this guy's writing way too fast, well, let me know. Okay, so x, y. So if x is, say, 0, then we plug 0 in here. For x, 2 times 0 plus 1 would be 1, right? So what would y be? It would be 1. Okay, what about 1? Let's plug in 1. 2 times 1 plus 1, that's going to be 3. So that's 3. And then 2, 5. Okay, so 2 times 2 plus 1, that is equal to 5. Okay, so when x is 0, the input is 0, the output is 1. When x is 2, or sorry, when x is 1, the output is 3. And when x is 2, the output y is 5. So let's go ahead and graph this line. Okay, we want to be at 0, 1. That's going to be 0 in the x direction. Okay, 1 in the y direction. So 0, 1 is over 0, up 1. And that's going to be right there. This is the point 0, 1, 1, 3, and 2, 5. Okay, so let me get rid of that. Okay, what about the next one here? Well, at 1, we want to be where? We want to be at 3. Oops, I wanted to get rid of that. Okay, we want to be at 3. Okay, well, where's 3? Well, let's see. Let me move this over a little bit more. Let's make it a little squarer. Okay, 1, 2, 3. Okay, so 1, 2, 3. We're going to need to go up to 5, 4, 5. Okay, so at 1, we want to be at 3. So 1, 3. Okay, and then at 2, we want to be at 5. Okay, and so now we just need to draw our line. This is a linear graph. So we're going to draw our line. I'm going to go to my tools. Where's my tools? Where are my tools? Maybe they're not here. Oh, there they are. Okay, I'm going to use my ruler. I'm going to cheat using my ruler here. Okay, and I'm going to be like, hey, if they don't go through your points, just make your points bigger. Okay, the line doesn't go through your points. You just make your points bigger. That's the way we cheat with that. Okay, just tells me that my point was probably off a little bit here. Okay, big points and a straight line. This guy here, right here, is called my y-intercept, which you're probably familiar with, and that's how we graph a line. Okay, let's graph one more. Okay, let's graph one more. Number 2, let's graph. Okay, let's graph 3x plus 5y equals 10. Okay, so I'm going to solve this for y, get this into what we call slope-intercept form. Okay, minus 3x, so we've got 5y equals minus 3x plus 10. divide by 5. I've got y equals negative 3/5 x plus 2. Okay, so this guy is going to be the slope, and this guy is going to be the y-intercept. Okay. Why is that the y-intercept? Because when x is 0, I'm at 2. When x is 0, I'm at 2. So that's the y-intercept there. And when I plug in an x value of 0, I get 2. Okay, what happens if I plug in an x value of 5? Right? At 5, well, this thing becomes negative 1. And what happens if I plug in a value of, negative 5? I'm using 5s here because the denominator here is 5, and that will cancel nicely. Okay, so if I plug in negative 5 in here for x, then that becomes a negative 1 when those two cancel. Negative 1 times negative 3 is positive 3, plus positive 2 is a positive 5. And so we just want to we want to graph this one. I am going to do a sloppy graph just because I really don't care on this one. No, I'm just kidding. I'm going to do a computer generated graph in a second. So one that's much prettier. But we can get a general idea, 0, 2, and then at 5, we're at negative 1. 1, 2, 3, 4, 5, we're at negative 1. And then at 1, 2, 3, 4, 5, we're at positive 5. So 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. And we're at negative 5, positive 5 is up there. And then we could just kind of draw our line, make our points big in case we didn't hit them. Okay, and we're good, right? It's kind of sloppy, but it works. Okay, and we can label our points if we wanted to. This is at 0, 2. This is at negative 5, 5. And this guy is at 5, negative 1. Now, again, I really didn't care about making this pretty because I'm going to make the next one pretty. Okay, I'm going to just do this on some software. Okay, we're going to use Desmos in this class. Okay, and I'm going to go to my Desmos graphing. Okay, so we've got our Desmos graphing here, and we're just going to plug in what we had. We had y equals negative 3/5 x plus 2, right? So I'm going to type in y equals, let me get my keyboard. Okay, y equals, okay, not capital Y. Why is my caps lock on? Okay, y equals, off. Y equals negative 3/2, or 3/5, sorry, negative 3/5 x plus 2, right? Plus 2. Okay, and then we're going to graph that. Oh, I didn't like it because I put in too many negatives here. Okay, boom. There we go. And there's our graph. Now, where's our, oops, what did I just do? Okay. There's our y-intercept is at 0, 2. Okay. We also had a point here, which is at, you can see that this is at 5, negative 1. If I could hover on it, it's at 5, negative 1. That's another point. And I'm just, maybe I'll just graph that point. 5, negative 1. Okay, and that labels that point. Do they want me to label it? Yes, label the point. There we go, 5, negative 1. Okay, and then we could also do 5 or negative 5, 5, and see that point also is on the graph. Negative 5, 5 is also on the graph. Okay, you want to label that one? Sure. Okay, and then we have this one as well. So there's the 3 points that we were dealing with before, right? Good. Okay. Let me quickly put up a couple more here. Okay, what if we wanted to graph a quadratic? Okay, what if we wanted to graph, say, get rid of my points. Say y equals x squared minus 1. Y equals x squared minus 1. Well, we could do the same thing. Y equals x squared. Just raise this to the second power, and then minus 1. Okay, and we get this guy here that's called a parabola. Okay, this guy here that's called a parabola. And we can see that there are 3 points, 3 nice points here that parabola goes through. It goes through -1, 0, 0, -1, and 1, 0. That is the 1 y-intercept and the 2 x-intercepts. Okay, 1 y-intercept and 2 x-intercepts. So let's translate that onto our notes. So this one was number 2, so I'm going to go number 3 in this case. Number 3 was, okay, y equals x squared minus 1. And we saw from the graph that at these 3 points, it was a parabola that hit through those 3 points. Okay, it was at 0, -1. It was at 1, 0, and -1, 0. Okay, enough said about that one. Okay, what about the fourth one here? Let's graph. Okay, let's graph. I can't write. Let's graph. Okay, x equals y squared. Now that looks kind of weird. Okay, x equals y squared. Does anybody have any idea what this looks like? X equals y squared. What you got for me here? Okay, it's a laying down parabola. Okay, and absolutely, Gabriel is correct. It's a parabola that is laying down. It looks like this. The parent function, y equals x squared, looks like this, right? Okay, that's the parent function parabola. Okay, but this guy, x equals y squared, that's the parabola laying on its side. We've exchanged the domain and range. Okay. Okay, we've exchanged the domain and range, and so what was x is now y, and what is y is now x, and so it lays down. Can you show us how you would write a table for number 3? Sure, absolutely. I would go like this, x, y. I would plug in 0. Okay, and so what do you get when you square 0 and then minus 1? Well, I get minus 1.
1.
Yeah, exactly. Okay, -1. Okay, what happens if I plug in 1 here? What's 1 squared minus 1?
0.
0. Very good. So this would be 0, -1, 1, 0. Okay, and then what about if I did -1? What's -1 squared? It's still 1, right? It's still 1. And so -1 squared is still 1, and so that's
0.
1, 0 again. So there are the 3 points that we showed on the graph. Okay, good question, Oscar. Thank you for asking. Okay. Okay, this guy, I could do the same thing. However, I'm going to say that I'm going to plug in y first and then do x. But then I have to make sure that I keep things. Well, maybe I won't do that. Maybe I'll just keep them. Okay, x, y. I want to work with y's though first. Okay, not with x's. I need to go backwards because the way this thing is working. Okay, so if y is 0, then what's x? Well, x is 0. So that's 0, 0. Right? If y is 1, then what is x? Well, it's 1. But if y is negative 1, then what's x? Well, it's still 1. Right? So this is at 1, 1, and at 1, negative 1. Okay, so this is not a function. This is something called not a function. Okay, it's a relation, not a function. This is a relation, not a function. Okay, but we can still utilize it, utilize its properties. It does have a point at 0, 0. It has a point at 1, 1. And it has a point down here at 1, negative 1. That's a negative. 1, negative 1. Okay. One, 1. There we go. Okay, it makes sense. Okay, we're ready to get on to something funner. I feel like funner is going to be in the dictionary soon, if it isn't already in some sort of Oxford dictionary. So, because I use it, so why shouldn't it be in the dictionary? My logic. Whatever. Okay, let's get onto something that's a little bit more interesting. Okay, and oh yeah, can we use Desmos? Could we use Desmos to graph this thing? I don't know, honestly. I don't know if it will allow me to. Let's see. It may not like it. But what happens if I square the y? If I do y squared. Yeah, it still does. It still likes it. Okay. And so you can see that, oh yeah, y squared equals x. Okay. It does go through those points. Okay. 1, 1 and 1, negative 1. Okay. How'd you get negative 1 for y on number 4? How'd you get negative 1? I just chose it. Those are the ones that I'm selecting. Okay, I'm working with the y's because those are the ones that are being squared. Okay. So you kind of think of as your domain and range reversed. However, that's kind of beyond the scope of this course. That's more for pre-cal students to work with. So I wouldn't worry about it. Just know how to graph it on Desmos and you should be fine. What graph were we looking at? This is the graph of x equals y squared. That's the graph we were looking at. Okay, x equals y squared. Okay, that's what we got. Okay. What else we got going on here? Okay, we're good. Okay, let's use a model, okay, to model some stuff. And then we'll get into some finance. Okay, so I'm going to leave that for there. Okay, number 5. Okay, use the model n equals 0.014t plus 2.88. Okay. Use this model. I'll just put a period there. Okay, where t is the number of years after 2004, and n is the number of participants in millions okay, in millions of female high school athletes okay, in millions of female high school athletes to predict, use this model to predict okay, the number of female athletes in 2017. Actually, let's make it 2021. Okay, athletes in 2021 because it's a predictive model. Let's try to predict the future. Athletes in 2021, not 2012. The world was supposed to end in 2012. I think the Mayans missed it by about 8 years. So 2021. Okay, so use the model where T is the number of years after 2004 and N is the number of participants, okay, in female high school athletes in millions of female high school predict the number of female athletes in 2021. Okay, so the first thing we need to do is find out, well, how many years after 2004 is 2021?
7.
Yeah.
17 years.
17, yeah, 17 years. Very good, thank you. Thank you for your class participation. I appreciate that. Okay, so that's 17 years, right? So T, what do you think T stands for? Okay. It's not, yeah, time. Thank you, Mario.
Yeah.
Okay, it's time. Okay, time, T stands for time here. Okay. Okay, so T is the time after 2004, so that's 17. So what's our model? Our model is N. It's a linear model. N is 0.014 times T, which is 17, plus 2.88. Now I'm going to pull up my calculator real quick. Okay, just take a minute to load. Okay, and I'm gonna calculate this out. Okay. N is 0.014. Okay, clear. Okay. See if I can get this to look a little nicer. That's better. Zoom. There we go. That's much better. Makes me happy. Okay.
Yes, sir. Are you muted?
We
Yeah, I don't
can't
know how
hear
that
you.
happened. I don't know how I got muted. So I don't know at what point in time that happened. So
Not like a minute.
must have hit a wrong key or something. Okay, so how long ago was I muted?
For like 1 minute.
For like 1 minute? Okay.
The 3.12 athletes.
Okay, so yeah, so it's just 3.12 million athletes. I mean, that's basically it.
Nice.
Okay? Does that make sense? Any questions on
Yes.
number 5 while I was muted there? Okay, so basically we're just using the model. We're plugging in the time, okay, 17 years into the future. Okay, it's a predictive model, and we generate the number of athletes, okay, using the calculator. Okay, let's do our application now for this. Okay, what's the application that we want? Well, the application that we want is we want to talk about compound interest right now. Okay, this is the function that we want to work with. Okay, compound interest. Okay, hopefully you are already familiar with compound interest. Okay, so this is a business application. But we're going to review it here in case you're not familiar with compound interest. Okay, if something is compounded annually, okay, then we use the formula or the function A equals, okay, P times 1 plus R to the T power, okay, where P is our initial amount, or called our principal, okay, principal, okay, our initial amounts. Principal means first, okay, our first amount. That's why the principal of a school is the leader. It's the guy that's in charge. He's number 1. Okay, so principal, initial amount. Okay, the R is an interest rate in an annual interest rate. Annual interest rate. Okay, usually called an APR or annual percentage rate. Okay, if it's an interest rate as a percent, it's called an APR. Okay, when it's like, oh, you can finance your home for 3.5%, that's an APR, that's an annual percentage rate. Okay, but we just say R is our annual interest rate, and R is a decimal, not a percent. Okay, it's a decimal. Okay, R is always a decimal. They may give it to you as a percent, but you have to change it to a decimal. Okay, annual interest rate and as a decimal. And T is time in years. Okay, T is time in years. Okay, so let's do an example with this guy. Number 6. Suppose, okay, $1,000 is invested in an investment fund, at 5%, compounded annually. Okay, how much is in the fund after 2 years? After 2 years. Okay, how much is in the fund after 2 years? Doesn't look right. 2 years. There we go. After 2 years. Okay, so we're just going to use the formula. We're going to say A is equal to P times 1 plus R to the T. Okay, so what's P in this case? What's our principal amount?
1,000.
Yeah, 1,000. Thank you, Lucero. Okay, it is 1,000. Okay, what's our rate? What's our R in this case?
0.05.
Who said that? Jess?
Yeah.
I'm gonna give you a shout out for that one. Okay. I don't do extra credit, but if I did, you would have got some. Okay, so yes, that is 0.05 as the decimal. 5% as the decimal is 0.05. It's not 0.5. Don't make that mistake. I've seen that made a lot in my life. Okay, it's 0.05 is 5%. So we're gonna 5%. And then what's T? Anybody? What's T?
2 years.
Answer.
2.
Aaron, was that you?
Yes.
Okay, Aaron said it's 2 years. Somebody else said it was 2 as well, but I didn't get there. It didn't register. Okay, 2 years. So we're just going to calculate this bad boy out, right? Okay. The girls like the bad boys, or so I'm told, until they want to have someone help them raise their children. And the bad boys don't stick around. Anyway, I digress. Okay, is equal to what? Let's just pull up our calculator here real quick, and we're going to go 1,000 times 1.05 raised to the second power. Okay, and I'm getting 1102.5. Okay, it was really not 0.5, it's 0.50. Why? Because we're talking about money. Okay, monies. Okay, monies. Okay, I always like saying the word monies because it always reminds me of Invader Zim. Okay, and that guy, he's like my favorite. So he's like, I'm done with my business. He's always had a thing for flair. And I liked his little flair, his little purple eyes and his green skin. It was good. Okay. Okay, so this is my money that I earned in my account at the end of a 2-year stretch. Now, had I just done simple interest, how much would I have made? If I hadn't compounded, how much money would I have made?
2,100.
Yeah, I would have made $1,100. I would have made an extra $100 off the 1,000, right, for simple interest. But because I compounded twice, I made more money, right? Because I compounded twice, I made an extra $2.50. So there you go. That's the power of compounding interest. Okay. Okay, let's look at compounding more than that, more times than just twice in 2 years. Okay. After 2 years, I would have made a certain extra $2.50 by compounding. This is simple interest. Simple interest. I would have made this. Now, how do I get simple interest? It's just A is equal to P plus IPR, right? It's let me think about this for a second. It's the total amount. The total amount is the principal plus the interest is equal to PRT. I'm sorry.
Is it 1 plus R?
It's this. It's P plus PRT. There we go. Okay. So that's my simple interest formula. You could factor out a P if you really wanted to. Okay. So you could say that it's the principal times 1 plus RT. right? And that would be my simple interest formula. I'm just saying, take my principal, multiply it times my rate, and then multiply it times my time. Okay, so I would make $5 every year, right? I would make $5 every year. So if I want, this is the interest that I'm making for simple interest, is the PRT, right? That's the interest part. So if I take my $1,000 and I multiply times the 5%, that's 50 bucks. No, that's not 50 bucks. Yeah, it is 50 bucks, sorry. It's 50 bucks. And then I'm going to do that twice, right? I'm going to double that. I'm going to do that twice. Okay, the P times the R times the T is going to give me $100 in interest. Okay, and then I would add that to my principal. So this is the simple interest formula. Okay, we don't really use simple interest in this course because it's so simple. Okay, that's why I had to derive the formula myself, because I don't really use simple. Who uses simple interest? I don't know. Right? People who are simple. 8th graders, that's who uses simple interest. Okay, 8th graders use simple interest. Right? So, okay. Gabriel, you read my mind. When do we use this formula? Well, that's exactly what we're going to do next. We're going to use the compounded interest formula. Okay? So if I want to compound more than once a year, okay, if I want to compound more than once per year, compounded interest, compound interest with n compounding intervals annually, okay, with n compounding intervals annually, then this is the compounded interest formula. A is equal to P times 1 plus R over N to the NT. Okay, so we add an extra variable, and N is the number of times I compound in a year. So if I compound quarterly, how many times am I compounding in a year?
4.
Right. How many, Enrique? 4. Yeah. Thank you, Jess. Thank you, Gabriel. Thank you, Enrique. Okay, it's 4 times. I am compounding 4 times in a year. Okay, quarterly, 4 times. So N is going to be equal to 4. Does that make sense? Okay, we're going to get into the power of compounding interest in a little bit later. Yeah, a lot later. Chapter 2. Chapter 2 is all about doing this thing to infinity and beyond, as Mr. Lightbeer would say. Okay, so A in this case, you know, again, quarterly would be this. So let's do the same problem that we just did real quick. This will be our last problem. Let's do the same problem we just did, but we're going to compound quarterly. Okay, we're going to compound quarterly. So $1,000 invested at $1,000 invested at 5% over 2 years, compounded, not annually now, compounded quarterly. Okay, it's compounded quarterly. Okay, so if it's compounded quarterly, then we have to use this formula because we have more than one compounding unit. Now, if you let n equals 1, if you let n equals 1, this just defaults back to the previous formula, right? If you let n equals 1, isn't this just 1 plus r to the t power? There you go. That's your compounded annually formula. But here, we're going to compound 4 times, right? So 4n is equal to 4 here. So we're going to go, oh, okay, A is equal to 1,000 times 1 plus 0.05 over 4 to the 4 times 2. T is still 2. It just means that I am compounding 4 times a year, which means I will have compounded 8 times in 2 years. So we'll have compounded 8 times, okay, in 2 years. So we will have compounded 8 times in 2 years. 8 times in 2 years of compounding. Okay, and my rate that I'm using, okay, my nominal rate, or the rate at which I'm compounding, is really not 0.05. It's 0.0125. Okay. N is the number of times I'm compounding in a year. T is the number of years. T is always years. T is always years. Right? N is the number of compounding intervals per year. T is always years. See, hopefully that helps. The nominal rate here is the 0.05 divided by 4. Okay, it's no longer an annual rate. It's a quarterly rate, right? Maybe I'll just put that as a quarterly rate. This is now a quarterly rate. It's based on the annual percentage rate of 5%, but we've divided it 4 times. We said, oh, instead of using a annual rate, we're going to use a quarterly rate based on the APR. And that's really what you do when you finance a vehicle. You're not paying an APR of 5%. What you're doing is you're paying an APR of 5% divided by 12, because everybody pays their car payment in monthly on an amortization schedule, and that monthly payment is a monthly interest rate. You are paying a monthly interest rate that's being compounded. You're not paying an APR. So they're actually kind of lying to you. You're saying, oh yeah, we're going to be paying APR. Well, no, you're not. You're actually paying a nominal rate, a quarterly rate that's being compounded 12 times during the year, and it's compounded for them because they're the loan officer. It's going against you because you're the one that's taking out the loan and you're paying this in interest on your loan. Okay, but this is going to be what we're doing here is a quarterly rate. Okay, and so this is going to be 1,000 times 1.0125 raised to the 8th power. The quarterly rate was 1.25%. It's no longer 5%. The quarterly rate, okay, is 1.25%. Okay, and it gets compounded. So you're actually getting screwed because it's not really 5% anymore. It's 1.25%, but it's compounded, which means you're actually tacking on more and more interest. The banks know how to make money. Okay, they do. And if you plug this into a calculator, you get $1,104. No, yeah, $4.49. So before we made an extra $2.50 by compounding twice, but we made an extra $4.50 by compounding 8 times. And you can see the power of compound interest there. The more I compound, the more money I make if I'm a lender. If I'm a borrower, it's the more money I have to pay out. But if I'm a lender, I like compound interest. And we'll talk a lot more about compound interest a little bit later. I'm over time by a minute, so at this point, I'm going to let you guys go, and I will see you back here on Thursday. If you have any questions or issues, come and see me during my office hour for this class only on Thursday at 5 to 5:50, right before this class. Okay? If you have any other questions that you absolutely want answered, I'll stick around for a few minutes to answer those questions, but at this point, you are dismissed.
Professor,
Yes,
Thank you.
do we have homework starting today already?
yes.
Okay.
Feel free to start on it. It's section 1, R1.
Good night.
Right.
Thank you, Professor.
Yes, absolutely. You too. Have a good day.
Professor, I have a question on the number 6, the Alton formula.
Yeah. One second. Let me stop my sharing real quick and I can stop my recording.
All right, no worries.
Professor, did you say that this recording will be live in YouTube by tomorrow, like 24 hours? Is that what you said?
Yeah,